All right. At this point, I'm hoping this is pretty familiar to you. We want to know how cells in your brain, right, also your muscle cells, your heart cells work. And we understand that they are these things called excitable cells. And we started with this notion that there is more sodium on the outside and less on the inside, more potassium on the inside, less on the outside, right? And this sets up these Nernst potentials, right? So I'm going through this quickly because we already talked about it. And these Nernst potentials compete to influence the transmembrane potential. So when we look at the transmembrane potential, we are measuring the voltage. Here we have our voltage inside. Here we have our voltage outside. And this is going to be our V transmembrane potential, right? So we're measuring a voltage across it. And what we discovered is that if you look at the voltage transmembrane over time, it is remarkably sitting at, this is going to be negative 100 millivolts. We'll put this at plus 100 millivolts. It is sitting somewhere near negative 100 millivolts, a tenth of a volt negative. And every now and then there is this spike that comes up, it comes back and comes down, and then there might be a little while later another one, right? And so these are our action potentials, and this is our resting membrane potential. And right there, you know, right in the name, right? Potential, like a voltage potential. Resting means what it's hanging out at of the membrane, right? And then something happens, this action, right? And understanding how these action potentials arise is fundamental to understand how the brain works, how the heart works, how muscle works, and also how neuromodulation works, right? So at this point, this is pretty familiar to you, right? So these are these spikes. And we've spent a bunch of time explaining how this model here, right, explains what's going on here, right? And specifically, to summarize, you know, we can move between EK here and let's say ENA up here. So these are sort of our boundary posts. And the membrane potential can approach EK, or it can approach ENA, or it can be somewhere in the middle. Whether EK or ENA is more important depends on these conductances, right? So for example, if this conductance goes to 0, then we only have EK, and so the membrane potential is going to, oh, did I write this wrong? ENA. Which was green? Green is, did I miss the colors? Yeah. I've also changed the, oh. This is fine. EK. Okay. EK, GK. All right. So what we have here, right, if this is all gone, well, it's only ENA and the V membrane potential, right? And in this case, it's positive from here to here. So the V transmembrane becomes ENA if this conductance goes to 0. If this conductance goes to 0, right, which is like having an infinite resistance, this goes away, right? And now the membrane potential is simply set by EK. And when both conductances are in play, we're going to be somewhere in the middle, right? So, and I've said before, if you go inside a cell in your body, you will not find a capacitor like this. You will not find, you go inside the membrane, you're going to find a little 9-volt battery, and that doesn't exist. This is simply a model, right? But this model does a very good job. And these arrows here, these sort of represent the fact that both GK, VTM, and GNA are a function of the membrane potential. So these conductances both determine the membrane potential and they're influenced by the membrane potential. And this is what Hodgkin-Huxley figured out, right? And what those simulations you were running were telling you. Okay, so that's reviewing everything we've done so far. Okay? So we have this, and we have this, and we have this behavior, and now hopefully we understand where these behaviors come from. Okay? But we need to add a little bit to the story. Because the cells in your body are not all little circles, right? Certainly not the neurons, and certainly not things called axons or nerves. So these are the wires that run all through our body. When my brain wants my hand to close, that signal is sent down a very long, narrow cell that doesn't look like a circle. It looks a lot more like a tube, right? So this is what we're going to call the axon. You might call it a nerve. It functions a lot like any other cable that you might see around, right? It transmits information. So when my brain tells my arm to constrict, that information is transmitted as an electrical signal this way. And if I touch something and I start burning my hand, that information is also transmitted to my brain along these axons, right? And so you need to understand that there is electrical activity going up and down these axons, right? And so right away, it doesn't look like a circle. It looks much more like a tube. And so we need to kind of update our model to capture what happens along these tubes. And in the process, we will learn about something called action potential conduction. Conduction what? Conduction along the axons and tubes. Right? And this is an essential part of building up our understanding of what's going on. Okay. So what I'm going to do is I'm going to add this cell. Let's say, let's work here. The room. Well, I'm going to redraw it. Here's our tube. And I want you to understand that this tube is made out of a membrane, a layer of fat just like this, right? So we can imagine that this is a piece of fat, okay? And so we have the inside of the tube, we have the outside of the tube, and this part here is the membrane. So you've kind of stretched it out like a straw at this point, okay? I'm going to attach our sphere that we don't here. So here I'm going to attach to the end of this tube. Right, is this structure that we've been dealing with so far, right? So this is the model of this structure. Let me redraw that model quickly. We're going to have a model that looks like this. Okay. And I'm drawing it in shorthand, right? Maybe I'll fill in some more details later, but you understand what I'm drawing here. And there is a voltage inside here, and there's a voltage outside here. And I'm going to call this, for reasons that'll become very clear in a second, location 1 and location 2, right? It's the only locations we've had so far. So here I'm going to do voltage in at location 1. Here's my voltage out at location 2. And so the V trans membrane, now defined at location 1, is this difference. I haven't really added, oh, no. I haven't added anything. What I'm simply doing is I'm simply annotating this as I'm calling this location 1, because obviously we're going to have location 2, right, in a second. I haven't updated anything. It's the same thing. But now there's this tube attached to it. How do we represent the tube? The way we represent that tube is we're going to cut the tube into segments. Are there real segments? Not necessarily, but I'm going to cut it into segments. And I'm going to call this segment number 2. I'm going to call this segment number 3. And I'm going to call this segment number 4. Right? And there's a reason I'm going to be doing it that way. Now, segment number 2, if I go inside of it, in this location, I'm going to have a voltage inside, but this voltage inside is not necessarily the same as this voltage inside. It's a different part of the cell. All right? So you have to accept for now that this voltage does not have to be the same as this one. And I have a voltage outside as well. Application 2. And so therefore I also have a transmembrane potential here. So what does that mean? If I took my voltmeter with my 2 prongs, right, and I measured a certain voltage here, and I get some value, like -50, and I measure it here, they don't have to be the same. It's like a different compartment, right? How would I represent that as a circuit? So what I'm going to do is I'm going to represent it like this. I'm going to keep this aligned here. I'm going to do this. And I'm going to say that I have a voltage in, at location 2. And I have a voltage out at location 2. And so I have a V transmembrane at location 2 that goes like this. So what does this resistor represent? This resistor represents this membrane compartment here. Okay, it represents the voltage across this. Now before I represented this as a capacitor. For now, I'm just going to assume that it's a resistor. We'll go back to representing it as we can go back as a capacitor. But I'm measuring a voltage, and I'm saying that this voltage is across a resistance here. All right? Now, it turns out that there is a connection from here, I'm trying another color, to here along the inside. From this location to that location, there's in fact a connection. If I had a balloon, right, and I put a straw on it, you'd be able to draw a connection from the interior of the balloon along the inside of the straw to the next point, right? They are connected to one another. Does that make sense? This represents that connection from this point to this point. They are connected, right? Something could flow from one to the other. I'm going to draw that connection as a line here. All right. So now I've connected this compartment to that compartment. I've gone from a physical representation of something to a circuit, a physical representation of something to a circuit. All right. And now a couple more little simplifications, all right? I'm going to assume that the V out everywhere is equal to 0, or you can think of it as I'm going to make this our reference. So what I'm going to say is I'm going to assume that V out 1 and V out 2 and all of them are the same. I'm going to make that assumption, right? That outside things are flat. All right, and I'm going to call that my reference, right? I'm going to call that, as a result, all the voltages are there. So what that allows me to do, as I'm trying to simplify this picture, is I can redraw these in a second. But what I'm going to do is I'm going to re-add in here that these points are the same, and they're in fact the 0 that I'm measuring. So it's V in minus 0 is V transmembrane, V in 1. V in 2 minus 0 is V transmembrane 2. Yes?
In the circuit representation, why is it we don't connect the other side of it?
From here to here? At this point, you can assume that this sort of is, if this is ground, then this is ground, then they're, like, electrically they are in the same spot. We will add something more, we will add more explicit things later. At this point, I'm trying to simplify, and then we will add. All right? There's only one more thing I need to do before I'm done. It turns out that from here to here, instead of thinking of it as a straight wire, I'm going to think of it as a resistor having some resistance. And I'm going to call that R in. And I guess to be clear, I will label this one, I'll call this R M. Okay, and now we're done. I made some simplifications. Now we're going to talk about what this means. What did I do? I had my initial model that we've been working with all along. But then I said, well, it's not a circle. It's like this circle with a bunch of a straw on it. So I drew the circle with the straw on it, and I divided the straw up into compartments. All right? And I said, what I'm going to do is I'm now going to say that this here is a representation of this here. Right? And if I do that, as we'll show in a second, I can keep repeating this process. I can add another leg, and I can add another leg. Now, the question is, why have we done it this way? Okay. I want to talk about, for those of you who had 4 or 5 with me, all right, my favorite circuit, right? The voltage divider, right? We did voltage divider. Well, let's review voltage divider, okay? And we're going to go through voltage divider as if I'm talking about something completely unrelated. And then right at the end, I'm going to surprise you by somehow connecting it to what we see here. But let's pretend to be surprised, okay, as we get to that point, okay? So when we talk about a voltage divider in circuits, we have a circuit that looks like this. Now this is our voltage in. I'm going to call this V1, right? I'm just going to call this V1, just for the heck of it, all right? I have 2 resistors here. I have to assign them values, right? Just for the heck of it, right? I'm going to call this one Rin, and I'm going to call this one Rm. But I don't want to be confusing, right? This could have been R1 and R2. This could have been 3 ohm. This could have been 7 ohms. This is very familiar to you from circuits. Just think about a circuit, right? And finally, I'm going to ask, what is the voltage here? And I'm going to call this V2. So if we think about this from a circuit's perspective, right, we get the following equation. We say, well, V2 is equal to V1 times Rm over Rm plus Rm. And so V2 tracks V1. There is a conduction, if you will, but it's not perfect. For example, if we want to be just to make it clear, if we want to be specific, if this was 100 millivolts, and I gave this a 1 ohm and this a 1 ohm, and I asked what is the V out here, right, what I'm calling V2, all right, I would say V2 is equal to 100 millivolts times 1 over 1 plus 1 is equal to 50 millivolts, right? So if I have 100 millivolts here, I get 50 millivolts there. Now, it depends, of course, on the resistors, right? What is true, though, is that this has to be smaller than that. There's no numbers I can put in here that doesn't result in some level of loss. Now, if this voltage suddenly goes from 100 millivolts to 0, then this voltage will also drop to 0, right? Because then I would get 0 times that. Or if this voltage suddenly goes to negative 100 millivolts, then I'll have a negative 100 here, negative here. What I'm trying to show you is that this voltage is tracking this voltage with a little bit of a loss, right? If, for example, voltage 1 went from minus 100 millivolts to 20 millivolts, and then back down to minus 100, right? So V1 now, it starts at minus 100, this circuits, we're not talking anything about action potentials, right? This circuit started, this voltage here started at minus 100. It suddenly went up to plus 20, and then it went down to minus 100. And I can ask you in circuits class, right? In circuits class, what would happen? It's getting messy here, but you know, V2. What would happen to V2, right? And if you're tracking, you would say V2 would do something that looks like this. It would go from minus 50 millivolts to plus 10 millivolts. V2 would also start negative, go positive, and then come back, but it would be damped. Okay, you follow me? So that's a review of voltage divider. A voltage divider, we didn't think about this in right? It transfers a voltage here, and it transfers a voltage down the line to another position. So if I were to take this more complicated compartment here, right? It's a more complicated compartment, so I'm just going to call it, I'm going to call it as a box. And I'll call it VTM1. All right, and by the way, I could have, we don't do it, but you know, we don't, I could have said, well, this is my, right, this is my, every voltage is relative to this reference, right? And this line is the same as that line. So you know, it's V1 is relative to this reference, and V2 is relative to this reference, right? We kind of assume, that's sort of implicit, but that's what was being done here, right? When I was writing V1, it was this point minus this point, right? And V2 was this point minus this point, but it was the same point. That's why everything became so easy. But it was in the background. So now I'm going to write this. I've replaced this with this compartment. And I'm going to write Rn, and I'm going to write Rm. And here I have V transmembrane 2. And look what we have done, right? Or nature, right? Or God, whatever. However you see it, right? Look what has happened here. All of a sudden, we can see that this voltage at this location, remember this is location 1, that's why I'm using this notation, right? Will be transmitted inevitably to location 2, right? Based on the same principles that we understand from voltage divider. Now, I had to do some stuff to get there, admittedly, right? I represented this as a resistor, and I drew, yes, right? So if you may not accept this, right? But if you're willing to accept this, right, we simplified further to this point, and now we understand that whatever happens here is going to be reflected here, but a little bit smaller, right? So I can draw here, let me see if I'll go back to black. If in location 1, I have an action potential that goes from, let's say, minus 90 millivolts to plus 20 millivolts. Is there 0? Nope, that's not our 0. That's where 0 is. Right, and this is location, this is VTM location 1. So now I'm going to draw VTM at location 2. We're going to use the same kind of analysis I've done here. And VTM at location 2 will look like that, where it's going to go from minus, well, depending on the values, right? It's going to be some value to some, but what I'm trying to show you here is it's reflected, but it has to be attenuated. It has to shrink a little bit. How do we know it's going to shrink a little bit? Because we know that from voltage divider. If you have 10 volts here, you're never going to get 12 volts here. You can't do it. If you have 10 volts here, you're not even going to get 10. There's some loss. Plug in any values you want. This quantity here is always less than 1. Now, you could say, can I get it close to 1? You could, but you're not going to get it to 1, right? Maybe you can get to 0.99, but there's always a loss, and there's a reason I'm emphasizing the loss. Okay, there's two concepts I'm getting across here. One is that it is transmitted, but the other one is that there is a loss. But we made it, didn't we? We transmitted information from node 1 to node 2. But as I've drawn it out here, we have a few more nodes to go. How do I model these additional nodes? What I'm going to do, hopefully it's not going to get too messy here, is I'm going to call this V in at location 3. And I'm just going to jump all the way ahead here. I'm going to write this as V in at location 4. Now, the outside maintains this assumption that it's 0 everywhere. Okay? And so for the purpose of, simplifying the picture, right? I'm just going to write somehow symbolize that this is all, the outsides are all 0 as is this one here. And this allows me to draw a picture that looks like this. And this point here, and now to be clear, I've replaced this with some resistance. This point here is also connected to this point here, and this point here is connected to this point here, right? Just like this bubble was connected to the inside of the tube here, the inside of the straw here is connected to the inside of the straw here, and the inside of the straw here is connected to the inside of the straw here. But I'm going to represent that connection as I did before by a resistor. And this allows me to create a model that looks like this. I'm now going to add a second line here, and then I'm going to add a line after that. And I'll do the rest in black, because that's how I started to. So this here is V in at location 3. This here is V in at location 4. And here I have current going out. Here I have current going out. And I'm going to call these RM, RM, Rin. I'll explain this in a second. And then here is V transmembrane at location 4. V transmembrane at location 3. I could draw it right here. I'll draw another version of it so it's cleaner. All right, this is messier than I wanted it to be. What I'm hoping that you see is that we have a voltage divider up until VTM2, right? And then from VMTM2 to VTM3, I have another voltage divider. Now VTM2 is the input, and it's just another voltage divider to VTM3. And then suddenly VTM3 is the input to the voltage divider, and I go to VTM4. I've coupled this circuit. There's a voltage here, and it gets transmitted, transmitted, transmitted. Yes?
So there's different resistance like between the inside of the cell, and then there's a resistance between like the inside of the cell and the outside. That's why they're not all
Correct. So I want to clarify a few things. This RN is not this RN, right? it simply has the same value. So if this is 1 ohm, this would be 1 ohm. And if this was 3 ohms, this would be 3 ohms. So I'm using the same notation because it has the same value. But this corresponds to this resistor, and this corresponds to this resistor. Similarly, this RM and this RM are different RMs. This RM corresponds to this membrane, and this RM corresponds to this membrane, but I'm assuming that they have the same value. And I think that's reasonable, because if you took a straw and you cut it into 3 pieces, the 3 pieces would roughly be the same. However, what I'm not assuming is that this RM and this RN are the same value. I'm not assuming that if this is 1 ohm, this is also 1 ohm. And so that's why I didn't just write R, 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 R. So I'm assuming I'm simplifying that these are all the same, and these are the same, but I'm leaving out this other bit of it, which I feel good about, because when we do voltage divider, we don't assume that these are the same, right? So I haven't made it any more complicated. So what I want you to understand at this point is that this is a source, and then we go through one voltage divider, then we go through another voltage divider, and then we go through another voltage divider, right? What is going to happen is that as we go, so now let's say this is the input, right? This is VTM2, and VTM2 is now the input. So what is going to be VTM3? Well, if I were going to write VTM3, it would have to be less, right? Because VTM2 is now the input to the voltage divider. VTM3 is the output, so it has to be less. And now, VTM3 is the input to the voltage divider, VTM4 is the output, so it would get even less. As I start to go down the tube, the voltage starts to drop and drop and drop, right? Because now, if you were to solve this explicitly, it's not exactly the voltage divider equation again and again, right? Because you'd have to solve the circuit together. But this is roughly what happens. So that means that here, I'm not getting much at all. Now imagine I don't have 3 compartments of the straw, but I have 100. By the time I get to the 100th end of it, there's nothing there anymore. And why is that a problem? It means that if I get a burn and the tube generates an action potential that is trying to transmit to my brain to get it, it will never get there, because the voltage will decay and decay and decay. It means that if my brain wants to send a signal to my arm to close, the cell here will generate a signal, right? But that signal will not make it down the line. This is a classic issue whenever you're dealing with transmissions down lines, right? We need the voltage, essentially the voltage inside, to be preserved, right? As we move all the way down the line, if you assume the voltage outside is the same, right? This is why you'll sometimes hear, when people talk about this, you'll hear them use the term cable theory. Because these models weren't initially created for neurons. They were created when people were using cables to do things like try to transmit information from, London to New York. And they were laying these cables under the ocean, but the signals were not getting from one end to the other. Because if you lay a cable in the ocean, it's like there's your straw, right? And why would the signal not make it to the end? Because whatever you set up in London, you know what I mean? And by the time you're halfway through the ocean, you've got nothing left. Does that make sense? So that's why cable theory is used. If you look up cable theory, you'll see something that looks like this. They won't even mention neurons, but it's the same theory. Because the axons are doing the exact same function as your Ethernet cable. Okay, it's doing. It's the same idea. There's a voltage here. Call it V in, and then I have a voltage, let's call it here V out. And I need to get it from one end to the other. So what is the solution? So it's not going to work. We're all dead, right? There's no communication between New York and London, right? But obviously it works, right? So and again, I know I've set this problem up very abstractly, right? But anyways, let's say this is the problem. How would you fix it? Any ideas? Maybe by looking at this equation. If I have 100 millivolt here, I can't get 100 here, right? But I could try to get 99, right? 99 maybe. So I lose. And how would I do that? Yeah, in the back.
By reducing the I.
Right. So let's go back to our discussion about voltage divider, right? If R in is very, very small, right? Then what would happen? Well, let's do another example here. We're going to say that this now, I'm going to use the same example, is about 0.01 ohm. Okay. So now I have 1 over 1 plus 0.01. Right? 1 over 1 plus 0 plus 0.001. And as a result, my result here, I'm just going to estimate it, might be around 99 millivolts. Okay, so according to the voltage divider equation, if this becomes very small compared to this, then this quantity, right, can approach, does not get there, but can approach 1. And if it approaches 1, then the drop from here to here is real but smaller. So if I were to redraw it, what would happen is that instead of going to this point here, it'd be smaller but less smaller, right? And then I would go here and it would be smaller but less smaller, and here smaller but less smaller, right? Let's say you lose 1%, okay? That may work unless I have 1,000 compartments, right? Right now we don't know how to estimate that, right? Because I have to give you a sense of it. But I'm going to tell you that it's sort of analogous to having 1,000 compartments. I mean, this is a really, really, really thin tube, okay? And so we would be modeling as thousands of compartments. Now there's something else you can do other than making Rn small. What is the other thing we can do to help? Yes? Oh, make the partition bigger. Okay, let me give you the quick answer and maybe we'll get it to the long. If I made this partition, if I said instead of calling this compartment 2, I'm going to call this compartment 2, right? Well, to be fair, I now have 2 resistors, right? The length of the tube is longer. So it turns out that it's a good intuition, but it turns out that how we carve out these compartments doesn't spare us the issue because things end up scaling. So if we make the compartments bigger, this value is bigger. And it turns out this value will actually be smaller. All right, and so we might get there when we derive. When you look at the derivation of the cable equation, you'll see how that doesn't help us. Which I'm happy it doesn't help us, frankly, because I mean, where I drew these lines is kind of arbitrary, right? But instead of making Rn small, I could also make Rm big, right? Because the two work together, right? So now I could say, well, instead of this being 1 ohm, I'm going to make it 1 kilo ohm, which will make this, 1,000. I'm doing this quickly. This will make this 1,000, right? And maybe now I'm at 99.9, right? So I know I'm doing this really quickly, but from voltage divider, I'm hoping you understand that this needs to be big and this needs to be small, and we want both things to be true. Yes?
How about you regenerate the signal?
And that's the next thing. You always ask me the question for the next thing. You're right. Regenerate. We'll get there, exactly. You want to boost it, is what you're saying. Yes. But let's say we don't, let's not get, right, let's hold the thought. So right now what we're doing is, right, nature, God is saying, look, Rm needs to be big and Rn needs to be small. If you go, and is that true? It's true. The inside of this cable is made out of metal, because Rn, the inside, should be low, right? And the outside of the cable is made out of rubber, right? Because Rm needs to be high. I mean, you know that. Like, you grab a power cable, you know that the inside is metal and the outside is rubber, okay? And that's because you want the thing to go this way and not through you, okay? Same thing for axons. The inside of axons has a relatively low Rn. It's actually salt water. It's kind of like the same thing that's on the outside. So nature has plenty of salt water, okay? So the inside is continuous. Like, we just go to fill the whole the tube up with salt water, which is, we're good for that. And the tube itself is going to be made of something resistive like fat, right? And so we actually have a situation where Rm is by design high, Rn is by design low, and so this drop off is even slower, right? We can just less. However, if you want to run a cable from London to New York, or an axon from here to here, you just can't beat this continuous loss. Even once you optimize these things, by the time you get to the 1,000th compartment, things are lost, right? So you can't run a cable from, that's why there's difficulty running cables from like London to New York or from whatever, San Francisco to Miami, right? No matter how well you make that cable, the signal does not show up on the other end. But someone made another suggestion. They said, well, what if along the way we boosted it? What does that mean? Let's go back to this blue situation here, right? So I got to the blue. It's compartment number 3. It's kind of small. Let's put values on it. Let's say it's minus, if it's attenuated in this way, I'm going to say it's minus 20 millivolts to plus 5 millivolts. It would be maybe more symmetric there, but it's like a little thing that showed up, right? A little beep like that shows up in VTM, right? Now what I would like to do is I would like VTM to take this signal when it arrives and increase it back up to 100 millivolt, right? What I want this compartment here to do, this part of the cell, is I wanted to do something very special. I wanted to sit there and I wanted to wait. It's wait. And then when this little signal comes along, which is a small deflection of a few millivolts, right? I want it to say, oh, I've been waiting for this moment, right? My whole life I've been waiting for this moment. I'm going to take that small deflection, let me keep it in orange, and I'm going to boost it back up to the full size signal. How much? Same as the original, 20 to minus 90. I want it to go all the way I want the full signal back. Because if I do that, right, I've restored the signal, right? Now if you can imagine, it might decay, boost. Decay, boost. And this is how they transmit signals from London, right, to New York. They don't rely on just a passive reduction, they build boosters. Now you can say, well, that's fine when you're running cables, right? But how in the world, oh, and let me give you some dimensions here, right? This axon here is approximately maybe 1 micrometer, a millionth of a meter. It's a very small tube, right? And the membrane, I mean, it's a fraction of that. It's just a little layer of fat, right? There are 2 little layers of fat, very small. It's like, right? It's like a molecular scale. You're telling me, excuse me, are you telling me that you want me to go into this, right? Whatever it is, right? So a few whatever nanometers I have to work with, and you want me to build into this an electrical circuit that is so smart that it sits around waiting for a signal to come in, right, which is a brief signal, by the way, quickly boosts it to a pre-specified level. How am I going to power it? How am I going to fit it in here? Well, it's already there, isn't it? It's obviously already there. It's this. It's just this. What does this do? You know already what this does. If this voltage, for some reason, goes up a little bit, right? And up to now, maybe it was a bit unclear what makes it go up, right? But if this voltage changes a little bit, these guys activate, producing an action potential, right? We know, to make it explicit, that if the cell is sitting around at its rest, right, and you tickle it a little bit, it doesn't do much. Maybe you tickle it a little bit more, still doesn't do too much. But then you tickle it a little bit more than that, and this process explodes. And you also know that it's all or none. You either go or you don't go, right? You transmit or you do not transmit. Sounds very binary, doesn't it? You transmit, there's a signal, right? There's a signal coming down, and that signal is either going to make it or it's not going to make it. And when it makes it, it just makes it as this one sort of bit of information that's coming down the other side. There's no, right, it's all or none. There's no half action potential. You go or you don't go. So what you have here is this model, and we reinsert it here. Yes?
So the booster is the same as the circuit model?
The same. I don't need to introduce, if we spent a lot of time on this, if you're sort of okay with this, all right, it is very easy for me to now introduce this. I could have done this instead. But I didn't want to start this way because I didn't think it would be simpler. I could have said, here's my circle. And I'm going to connect it. Let's just start with another circle. Nope. Anyways, so here is cell 1 and here's cell 2, right? Or you can call it compartment 1 or compartment 2, right? So I've taken two of these and I've connected them like that, right? Okay. What would be the circuit model of that? Let me redraw it. So I'm going to have C sub m. This is one of them. This is the other one. Okay, now, there's a potential from the inside here to the inside here, right? Now this is V in 1 to V out 1. And then there's another cell here. So I'm going to call this V in 2. And I'm going to call this V out 2. And so here is V TM 1. Here is V TM at location 2. Right? This difference is represented here, and then this difference is represented here, and I'm keeping my inside on the top. Right? I could have done that. I could have started the lecture today like this. I'm just going to have two of them. And then how do I represent this? I'm just going to add a single resistor from here to here, so I'm going to draw this. And I'm going to call this R in. Right? And that's it. Right? One of these, add another one, pretend like they're independent, but suddenly I'm going to add a little bit in the model where this one communicates with this one. And so what you're going to see is that if I get an action potential here, if this one goes off, right, that information, and the last thing I did for simplification, right, is I grounded the outside. I'm going to assume these are, whatever they are, I'm going to assume they're the same. Right? And now what would happen is if I get an action potential here, that voltage will be transmitted over here, and I could get an action potential here. And then, of course, I could add another one, right? And another one. Right? I could do circle, 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 right? I could have run the course, but I thought I wanted to present it this way because I wanted to anchor you in voltage divider. I wanted you to see that here it's a bit hard to see that this is a voltage divider. Right? It's a bit hard to see it, right? Because you wouldn't think of, okay, you say, well, okay, all of this, what do we call it, is our V1. And all of this, is our V2, and they're connected like that, right? And this has, it's complicated, but it has an internal impedance. So it is the same. There's a source, there's a connector, and here's the response, which then becomes, of course, the source for the next one, right? And so you can see here what happens is you get a pop, a pop, a pop, a pop. And now you can go from London to New York, and you can go from here down. Yes?
Is that the nodes of Grandview? It's like concrete?
Again, you're getting one step ahead, which is it turns out there's some additional icing on the cake, where it's sometimes, here I've drawn it, both in this case, well, the way I've drawn it here, you have some areas with boosters and some areas with not, okay? Which is not unreasonable, depending on the axon you're looking at. So in this case, you would have sort of these would be called your nodes of Ranvier, and these would be more like the insulation passive transmission components. They might be wrapped in different types of other cells you may have heard about. You know what I mean? Myelin and things we'll get there. So you guys you're cluing ahead. But it's going to be very easy to talk about all those things if you understand that what we're really talking about is a voltage divider with a boost. Voltage divider with a boost. Does that make sense? And if you think about it, we haven't gone too far away from this. I've just added another resistor. Or if you want, a voltage dividers. And then I went back to it, right? So as long as we're good here, and this was a lot of work conceptually, you can see that we're using the same framework. Does that make sense? And we're going to always use the same framework because it's really powerful. Okay? So now, when you're doing experiments with your TENS device, some of you realize that if you stimulated, you could get a finger twitch, right? And you're not trying to move your finger, right? You can call it an involuntary, right, muscle twitch. Why is that? Well, there is an axon, right, that it's running, or maybe it's starting, wherever it's starting, right? It's running out along my arm to my finger, right? Now, if you zap the axon here, right, if you zap it in the middle, right, it still goes. You don't have to start, if you look at this picture here, if I started here, would it still go to yes. When I stimulate here, this axon doesn't know that the signal didn't come from my brain. There's a little piece of membrane sitting here, and what does it do? It's just sitting there, waiting, waiting, waiting. When will my moment come? And suddenly, it gets activated, right? Because you put in electricity. And it thinks, this is my moment. So it goes off. And once it goes off, the next one goes off, and the next one goes off, and then it gets to the finger, and the finger moves. No one told the finger that the brain didn't say twitch. It's the same information. That's why we can stimulate here and make this finger twitch move. Now, it turns out that there's different fibers running to different fingers, right? So depending on when you stimulate, you can move different fingers. But we can explain that once we have this model in place, it's very clear, right? If you stimulate, if I were to add more, You don't need to start in the beginning. You can start anywhere. I can start here. That explains it. Same thing with feeling. When I press and I burn, that information is being transmitted along an axon. This is a different axon that goes from here, and eventually the signal will go to my brain, right? If I stimulate here, right? Sometimes did you feel it somewhere else? Right, so you stimulate here, maybe you feel it here, that makes sense, but you might also feel like your finger tingling. Why do I feel my finger tingling? No one's touching my finger. Because there's an axon traveling from here, going to my brain, and my brain thinks, oh, that guy comes from the pinky. I'm feeling tingling in my pinky, but you're not feeling tingling in the pinky. Right? You are faking it. Does that make sense? Now let me ask you a question. So now I have my hand. One, two, three, four. Now, there are some axons that travel and communicate information this way. We might call them efferents or motor axons, and they're transmitting information from the brain to the hand. There are other axons that are transmitting information this way. They're called afferents, right? Or sensory. Turns out the body has decided to use different tubes for information going this way and going that way. That's how the body is designed. Makes sense, right? Like different channels for different bits of information. So let me ask you something. If you stimulate this here, you zap it, right? And you feel it, right? So that means that the information went this way, right? Right? It's the natural way, right? Will it go this way? So this is a sensory system, right? It's when I touch the finger, I can feel it, and when I zap it, I can feel it, right? But when I zap it, will it go the other way? And I want you to answer that question just based on this circuit model. So now I'm asking you, I bring this up to 100 millivolt, right? And now I'm saying, and let's say this is towards the brain, right? This is the normal way, right? So this is towards the brain, and it's going to propagate. Will it also go the other way? What do you think? If I stimulate this one goes, right? Let's say this is the normal flow. If this one goes, will it come back at me? Yes?
Does it depend on the direction of the current?
It could, but does this circuit give us the direction of the current? That's the question. You might say, correct, but does this circuit give us the direction? Or does the circuit say, there's no directionality built? Does this circuit have, it's an interesting, does it have directionality built in? If I stimulate this, will this go? If I stimulate this, will this go? If I stimulate here, will it go off in both directions? But I know you don't like that because you're saying, well, that's not right. That's not how God made it. It's supposed to go one way. But I'm asking you, when you do tens on your arm and you feel it, is it also going the other way, the wrong way? What do you think? Yeah.
Would the fact that you're feeling it mean that it is going?
So if you're stimulating the sensory, so it's going this way, which is the right way, would it also start traveling like the non-normal way, like where the body thinks it came from? Or here's another example. If I stimulate the motor, right? So these are axons that go this way, right? That's their job. Their job is to transmit information from here to here. So I zap here and the finger is twitching. Is it also traveling back? Even though that's not a sense, I can't feel it, right? It's not a sensory, but it's going like the wrong way down the line.
How would we know if it's going, like, are you telling us that it would be?
I'm asking you first purely based on this circuit. So now I'm saying you're an electrical engineer, and I've shown you this circuit. I've explained to you how this circuit works. It has boosters. I know it's very messy. And I'm asking you, if this booster activates, will it go both ways, or will it only travel the way it's supposed to? What do you think? Raise your hand if you think it will go both ways. And everyone has to raise their hand one way or the other. Raise your hand if you think it'll go both ways. Raise your hand if you think it'll only go the way it's supposed to. But why do you think, okay, so why do you think it's only go the way, why do you think it's only go the way it's supposed to? Just because that's the way it's supposed to work?
I mean, in my head, I imagine it that, like, it travels through the afferent, gets to the brain, then goes back down to the
Oh, cause, oh, I see, it'll come back this way, it'll bounce around. Yeah. So the answer is that it will go both ways. Because this circuit model is correct. This circuit model predicts that when you stimulate an axon, boom, it goes both ways. It goes the way it's supposed to go, but it also goes the opposite way. And you could say, well, what does that mean? It's something that perhaps in some situations we can take advantage of. But it will go both ways. The axons, no axon that I know has a built-in way, like there's no diode or something here. No axon I know can control which way it goes. You can say, well, why does it not normally go both ways? Well, because normally it's depending, normally the sensory ones don't go until I feel something, and the motor ones don't go until my brain goes. Yes?
When you are stimulating tens just a skin electrode, is it reasonable to assume that you're actually only isolating one line? Or would you assume that
Okay.
when you're applying that gradient, you're crossing or tapping into both?
So now we're getting into like the next big thing. Let's look at our hand. 1, 2, 3, 4. Right. We now know, I'm going to draw in different colors, that this hand, I'm going to just draw the tubes as lines, has a whole bunch of tubes running in it. And I'm going to say that some of these tubes are motor, and they're supposed to transmit information this way, right? And some of them are sensory. So normally they're going this way, right? So if I feel something, one of these guys is going. And if I move something, one of these ones is going. Now, here we come along with our TENS device. Right, I'll draw a lightning bolt. All right, so this is our current from our TENS device. I stim. What are we doing? Well, I can feel it. So I guess I'm getting some of these. But sometimes I get involuntary motion. Of the ones that I feel, is it both the blues? Is it one of the blues? Right? This is the question you're getting at, right? And I have yet to give you the information to address that. So that is exactly what we're going to address next. So what we have done is we've started with, let's think about a single cell. And let's think about it putting our TENS electrode inside the cell. And that's what you were able to do, right? Remember, this electrode was inside the cell. Right? And then I said, it's not exactly a cell. It's more like wires. It's the right way to think about this when you're doing peripheral stimulation, is that you really are stimulating wires. You're not going to find a neuron that looks like this. They're elongated. And so we're going to think, but we have a very similar model, right? And we're going to do that as well. And it turns out that if you put your electrode inside the cell, you can stimulate just this guy, and it will go down the line. And if you put your electrode just inside this one, it's only going to stimulate this one. But now, something's off. Our model now looks like this. I'm going to draw it shorthand. So this is one compartment. Here's our next compartment. I shouldn't draw anything shorthand, but I want to just set this up, right? Here's the next compartment. Right, these were our compartments, right? Right, this is compartment number 1. This is compartment number 2. This is compartment number 3. It goes on and on and on. This was our R in, to be clear. Right, this was our CM, CM. Right, this was the model we had before, right? So I drew this very, very quickly. I hope this sort of makes sense, right? This is this very, very compressed version of this, right? But our stimulator is not, is here. We don't, it's on the outside and it's far away. It's like I have this, and then all the way down here, I have this. There's this disconnect, right? And you can say, well, what I want to do is I want to take this wire and I want to put it, this side is inside. I want to take this wire and I want to put it inside, or in, you can't put it inside. You can only have it outside, all right? So what we need to do is we need to understand that in some situations, this current can come out, travel to the cell, and go through it. This is now the outside. We are now in a situation where we need to realize that we are coming in from the outside, and we have to push current from the outside into the inside. All right, and that is a very, very big conceptual point that we're going to spend a whole lecture on, but it's exactly what you're getting at. And once I do that, I can try to answer the question of, will this one go or will that one go? But what I really want you to understand is, up to now, we have never done that. I've always let you cheat. I've always let you put your current source here. You had access to the inside all along. And I'm saying, nope. That works when you're running your little Hodgkin-Huxley simulator. Good for you, biphasic charge balanced, right? Good for you. You don't have this point. You don't have access to this point. You're on the outside, right? And so what I need to do is I need to give you another equation. And that equation connects this to this. And once you have that equation, now you're going to have all the pieces, right? But there is a conceptual piece there that's really critical, right? That's really critical. Any more questions, though, on just this sort of, on just this concept? Yes?
We had talked about whether or not it would go one way or both ways based on the circuit model by itself, but when you introduce the TENS device, since it has a directionality to it, whereas our model didn't have one, wouldn't it force it to just go one way?
How does the TENS device have a directionality in it?
Because it flows I guess it's like between, it's bound with like...
Oh, it's physically bound, correct. But when you put the TANS device on your arm, you have both efference and afference. And in fact, depending on how you set it up, you can produce twitching or sensation or pain. So there's still something missing here, and I'm not trying to hide it from you. I'm more just saying I have not given it to you yet. There's another equation. And once we have this the equation that couples this to this, we will actually have the full solution, right? And we'll be able to answer these more interesting questions, okay? But this doesn't make sense if you don't understand this first, right? That we're talking about tubes and not circles, right? Any more questions? Yes?
So in one, like if we're looking at the circuit as to be like one type of like neuron, like a motor neuron, you're saying that there's, in that one neuron, when we stimulate it, there's current going in both directions, even if it's meant to be like one, like...
What I'm saying is, yes, when we zap it, let's say now I haven't explained why, let's say we zap it here, in the middle of the arm. We zap it here. And this thing discharges, now we get an action potential here. Let's say normally, let's say it's sensory, so it would be transmitting this way. Let's say that's this way, right? And that will happen. But there's absolutely no reason why it's not going to go back this way in the sort of, might be called like the anti-direction, right? It's the anti-direction. It's also going to travel this way. And you may say, well, that doesn't matter to me, and it may not matter, or it may be something that we can take advantage of, even though it's not natural. But it does happen inevitably. And that's the idea. We have no way to, this notion of making it go one way and not the other is actually something that neural engineers have worked on getting to work. So it's not impossible, but it's certainly, if you just use your TENS device, it's going to go both ways. Yes?
The natural thing, I'm stuck on like why it would be natural for it to go one way, because even if I'm moving, right, I still need to feel the space that I'm moving through, or like if I'm moving to hold something.
So when you're moving, you're obviously getting sensory feedback back as well. That is being transmitted, though, by different wires. So the wires that are transmitting the sensation are specific sensory wires, afferent, that are traveling this way. And there are separate wires that are transmitting information this way. Now, if you're saying, well, who puts all that together? God, nature, science, or your spinal cord, or your brain, right? So all these wires, the ins and the outs, are converging in your spinal cord, right? In your brain, and then your brain is doing the work of saying, I'm feeling pressure here, I'm feeling something there, oop, I'm tilting, I'm seeing. This is all my sensory axons coming in, and now I'm going to start sending information out. Flex this muscle, put your hand out. But those are different wires, if you will, as I'm explaining it here. Those are, right, those are, the body uses different channels for in and for out as a general rule.
I guess what I'm asking is, do they operate on a delay, or are they simultaneously?
Oh, the timing. This, we'll talk about, this is not an instant process. All right, this process here can take a few milliseconds. So from this burn to that information getting here can be a few thousandths of a second. And then my brain has to process it, and then it has to send information out. So I would say it's fast, but not instant. Okay, let me finish. Why does the brain use electricity? Why is this electrical? For example, I could do this. I could have, when you touch my finger, a little cell here squirts out some green dye. And then the green dye slowly moves. At that point, my finger is burnt off. And then by the time it gets to my brain is like, which finger was it? So the reason the body is using electricity is for two reasons. One is the speed. It's really, really fast. It's fast. So we use it. Two, you can have multiple channels, right? One cable, right? One cable, right? One nerve can have many, many different axons in it. And each one is operating independently. So when this finger goes, it gets to my brain quickly, and my brain knows that it's this finger. It's the analogy with cable theory is really, really strong. Speed, right? Multiple channels. And this almost like binary level of communication. Yes, no, right? It's all built into your nervous system.